Okay, the next great adventure is to explore how partial depolarization can affect nonlinear optical measurements. And how do we correct for it, more importantly, to back out molecular level information in things that either scramble polarization either from the source itself or from interactions preceding or following the generation of the coherent signal. And these happen more commonly than you might think in microscopy measurements. So to work on a framework for treating partially polarized measurements, we'll have to deviate from the Jones matrix and Jones vector formalism and introduce Mueller matrices and Stokes vectors. And before we extend these into nonlinear optical measurements, let's first get a nice solid baseline reference frame in terms of the connections between Jones and Mueller matrices in linear optics. So just to make sure we're all on the same page, the Jones vector is a 2 by 1 vector that with two complex valued elements that describe collectively the polarization state for a purely polarized signal. Now, by purely polarized, I don't mean linearly polarized. This could be purely circularly polarized or purely elliptically polarized, but it has a pure polarization state. And we can think of Jones matrices as polarization transfer matrices, where we put in a particular Jones vector and get out another Jones vector. Again, as long as this is a non-depolarizing interaction, then both the incident and exiting fields can be described using Jones vectors. But if we introduce the possibility of partial or complete depolarization, then now we need a more general formalism. And the more general formalism is the Stokes vector and the Mueller matrix. So the Stokes vector, which is given by S over here, is based on intensity differences rather than field differences. And as a result, it's always purely real valued in terms of its entries. And we generate the Stokes vector, in the limit of pure polarization, you can connect the Jones vectors over here on the right to the Stokes vector through this transformation matrix, bearing in mind you end up taking the Kronecker product of those two, which is given by this product right here, to build a 4 by 1 product of electric fields that then translate over to the 4 by 1 combinations of intensities describing the Stokes vector. Excuse me. So in linear optics, if we want to build the Mueller matrix, again, in the most general sense, in the presence of partial depolarization or complete depolarization, then this is now a 4 by 4 matrix connecting the 4 elements for the input to the 4 elements of the output in the most general sense. Again, it's actually very useful, though, to connect this back to the purely polarized component in terms of the Jones matrix. And in that case, we want to find a way to bridge these two descriptions. And the way to do it is actually pretty straightforward. If we think of the Stokes vector and relate it in terms of the output fields, it's given by this expression, which we just got from the previous overhead. That's this equation right here. So we can then substitute the chi j, the Jones matrix times the incident electric field for the outgoing electric field in this equation, and you end up with this nice equation right here. There's a really very useful relationship of A times B Kronecker C times D equals A Kronecker C times B Kronecker D. If we use that relationship in here, then we can rewrite that equation in this form. And once it's in this form, we can now substitute for the incoming electric fields. And those are given by basically what it's the inverse of this equation here. So we have, let me show you what I mean. We have S in equals A times E in. And so therefore, this Kronecker product of electric fields equals A inverse times S in. So we substitute A inverse S in for each of these electric fields. Actually, for this combination of electric fields, and then you have something that reduces down to this form, where you now have an output Stokes vector for an input Stokes vector, and everything inside this red box is now your Mueller matrix, and that leads to this equality down here on the bottom left. So that's a way to, and that this again is just describing the purely polarized component to the Mueller matrix. There can also be depolarizing contributions that cannot be recovered from the Jones matrix approach. So how do we handle those? Well, one very simple minimalist way, if we think about the simplest possible way to treat something that is partially depolarized in the generation of a Mueller matrix, we can think of it as first starting out with the purely polarized component given by what's inside this brackets, and then an additional purely unpolarized component. And for an isotropically unpolarized system, the 0, entry in the Mueller matrix will be non-zero. And what that means is basically, if you go back to what the Stokes vector is defined to be, what that means is for something that is completely depolarizing, no matter what you put for the input, only this first term here is going to be non-zero, because that's going to cancel out in an isotropically scattering system. That will cancel out, and that will cancel out. So you'll be left with just the S0 no matter what your input is. And that leads to that form for the Mueller matrix. So we have a system that's partially depolarizing, and we can handle that partiality by introducing a depolarization parameter alpha. So in the limit of alpha equaling 0, then you have purely polarized interactions described by the Jones component, and the limit of alpha approaching 1, you have something that only generates S0, the S0 for the output irrespective of the input. And so anything in between we can treat by just scaling between these two extremes in a practical system. So why bother going to this simple model-based description? Well, the advantage is really in the difference in the number of free parameters. In the case of the Mueller matrix, we have 16 real-valued components, but the Jones, we have 4 complex components. So if we can, there's a huge advantage in terms of the number of free parameters in the Jones description for a polarization transfer element. So if we use this model, we start out with the 4 complex terms in the Jones description, and then we add a single real-valued scalar for alpha. And that really only adds just a small additional amount of complexity to the number of elements that we're trying to pull out. And yet from that, we can recover all 16 elements in the Mueller matrix. So the advantage of using a model for describing this is really one of simplicity and parameter reduction. All right, and that's where I'll stop for now, and we'll head into the next topic next.